Yeah, hi, welcome everybody to the final talk, I think, of our team for the medical 3D interactive segmentation challenge. Um, Basically, we thought we really would like to, first of all, make sure that we are using all the information. So use the 3D bounding box, use all the clicks, use all the previous segmentations, and make sure that we start from a very good baseline that we don't have to start from scratch. So that's why after also the April 15 presentation and so on, and even before that, we saw already this NN Interactive looked very promising to us. So yeah, we kind of started out with the NN Interactive baseline. And we had also the idea because the original NN Interactive V10 had like 2D slices and didn't have 3D information for the bounding box. So we thought, okay, maybe we can get better by using the 3D bounding box that we have in these kind of challenge. And one of the problems was also to kind of know, yeah, how to generate the relevant like correction clicks during training. And yeah, we of course we dynamically generate the clicks during training. We tried kind of some different approaches, but in the end we find that maybe unsurprisingly, if during training we are doing exactly the same way that the clicks are generated during evaluation, that was definitely best in our validations. And we also just said we try to find a training loop that is very, very simple and robust. And that's why we usually only generated a single click. So we didn't go through several clicks or anything like that during training. We really just said we either do the training directly on the initial image and the bounding box, or we say, okay, once we have done one predicted segmentation from the network, we feed it back in and we make a single correction click. And because we only trained like unlimited resources on a single GPU, we did not back propagate through both steps. Rather, we just took the previous predicted segmentation as an input, we stopped the gradient, and we only back propagated then through the second phase in case we simulated one click. Um, yeah, so yeah, the full training pipeline yeah is based around this NN interactive model. Of course, the NN interactive model also has some additional channels like for scribbles and so on that we didn't use here then at all. We just used the positive, the negative clicks, the bounding box, and as I said, the segmentation attempt or the previous segmentation in case we would simulate a click in that particular mini batch during training. Um, yeah, and an interactive inside, it's based on a residual UNet. They also kind of in the NN unit training, they use this deep supervision where they also make some candidate predictions from the earlier levels. We did not actually use that. We found that when we start from the NN active V10 weights, we don't really need to use the deep supervision. We can still get relatively stable training without it. And yeah, and also there was of course something during the competition that kind of determined what we did. Initially, we were just using these NNactive V10 weights and focused more on the post processing, and we were looking a bit into fine-tuning the modality-specific models, but due to the change in rules at the end, because of the new NNactive baseline and so on, and the request for us to definitely fine-tune the whole model, we focused on fine-tuning a single model for all the modalities, starting from the NNactive V10 And we first also tried to use the NN unit training code. We may have made some mistakes there. We found out later in the pre-processing, but in the end, since we kind of struggled to get it to robustly improve the performance, we just wrote our own very simple training loop. We removed all augmentations since we found that they were or that we at least we didn't see overfitting even if we didn't have any augmentations. We also stick to very basic kind of hyperparameters like 10 to the power of -4 for the learning rate of LMW and 10 to the power of -5 for the weight decay. So we did not perform like any sophisticated optimization there. As a losses, we used the kind of relaxed or smoothed dice loss and cross entropy and then some linear combination, I think with a weight of 10 on the dice loss. So we kind of focused on improving this relaxed dice loss. One thing we did later on after training was to look a bit at just very simple post-processings. So in the original NN interactive code, they just iterate through all the classes, and then any class that has a probability above 0 at a certain pixel is chosen as the predicted class. And if there are multiple, simply the last one is chosen. So we thought, okay, it should definitely be a small improvement if we actually collect all the probabilities for all the classes and then take the highest one. And additionally, we also compute like a probability for the background class as the product of all the negative probabilities of all the other classes. So one minus the probability of each class. That's kind of on the bottom of the slide here. And then we take the maximum of that. So it could be either the background class or any of these K classes that are present in the given image. And we find that this kind of simple post-processing, of course, one could do more, but this simple one at least kind of reliably should improve the dice score a little bit. Yeah, we also see that kind of in general, this one-click training works for us. Like we see a consistent improvement also over multiple clicks, even though we only train with a single one. You also see here already, I will talk a little bit about it, that we are much worse on the MR than the other images on the validation set. And yeah, you see here, if you take the average across everything, then actually we are kind of somewhere in the middle of the baselines. But then if you break it down by modality, you see that the problem is really the MRI. Actually, on the PET and the ultrasound, we are best. So we are also better than the NN interactive baseline that was released later. For microscopy and CT, we are in the second place among these baselines, so worse than the NN interactive, I think, but better than the others. But for the MRI, we are quite worse and by quite big margin. And yeah, here's kind of the same results again. And what we found that our model in the end really struggled on the validation set. Now we don't know the distribution of the training set, how much is the problem there, but on the validation set, we saw that it really struggles on the cases without bounding box. And unfortunately, we realized we also kind of submitted the wrong, let's say, checkpoint. We had a checkpoint where the difference was not as drastic, where it was performing a bit better on the bounding box. So it seems that in our training, it's just very, very unstable on those cases without bounding box. What we did actually, we just simulate a bounding box like in the center of the image, since that seemed to kind of work, but it seems that's not a good way in general for these cases. Yeah, here are some like just examples that you can also see in our paper of good and bad segmentations. So you see for the CT, for example, a very excellent one, and then that really fails fairly drastically on the bottom. Here for the MRI, as I said, for the MRI, we have like the worst performance across modalities overall. Microscopy, yeah, worked much better. Even the worst one here still has a dice score like above 50%, and the same for PT. And ultrasound, even the worst one, still even above 70%. So yeah, the limitations kind of really, I think we have this problem with the cases without bounding box. I don't know if this information is somehow available now, how much this actually exists in the testing set, if this is a reason for, let's say, a drop in performance for us or not, also on the test set. But definitely, I think we need to deal with them a bit differently, maybe also incorporate them during training. We didn't incorporate any examples without bounding box in training, I think. Also, I think if we had more time, or if we want to use the time now, we could look a bit more at more sophisticated post-processings, maybe even train some post-processing model. And like many others said, of course, we could look at training more modality-specific models, like fine-tune the base weights per modality. Yeah, I think that's was all I wanted to share. And this is the report and the code.